So just morning, everybody. We'll just wait a few minutes to allow everyone to get in, and then we shall commence and start with today's webinar. Okay, right. So we'll get started now. I think a few people will join as we carry on. And yeah, good morning to everybody. Welcome to today's webinar. As you can see from the screen, around CAD modernization using simulation-led design within Creo and Ansys here at PDS Vision. Can you move on to the next slide, please? So we're running a number of webinars over the coming months, and we've had some previously in May. As you can see, those are available through access on our website. I think you just have to enter some details in, and you can gain access to the recordings. Today's will be recorded as well, and made available, and then in a couple of weeks in end of June there you can see we have one looking at what's new in Creo 12. Next slide, please. So yeah, my name is James Latham. I'm head of enterprise sales here at PDS Vision, which involves it encompasses our simulation and systems engineering software. That covers the Creo and Ansys toolset and some specialist tools in manufacturing simulation as well. And my colleague and main presenter is Oisin Wilson, who's one of our simulation engineers here, based just outside of Manchester. Very, very quickly, you're probably all aware of who we are, but PDS Vision are a pretty global business. We joined them as a company several years ago. We're based, I say, just in Manchester. We have another office in the UK just outside Cambridge. We're headquartered in Sweden, and we are very heavily involved in digital transformation, looking at data control, data creation through CAD, managing lifecycle management, and simulation, digital testing, digital simulation of a range of products and range of scenarios involving structures, fluids, electromagnetics. We also look at reliability and functional safety as well. Next slide, please. There we go. So really our forefront and the main two products that we resell and are partnering with for a long, long time is PTC and Ansys, both US companies involved in the digitization of engineering and product development and product improvement. And, you know, we work with them very well, and they themselves work together very well. They have a great synergy. They make sure their products can work together and, you know, form a great digital thread and a digital process. So really this gives a very quick overview of, I suppose, all the traditional or the ideas of what a digital system and digital thread looks like. And today's really is highlighted there in focusing on simulating and understanding how a product works. I'll hand you over to Oisin now.
Thanks for that, James, and thank you to everyone for joining us for this webinar here today. My name's Oisin Wilson. I'm a simulation engineer here at PDS Vision. And today we're going to be taking a look at two product lines that have come about as a result of the strategic partnership between PTC and Ansys, namely Creo Simulation Live and Creo Ansys Simulation. I'll start by going into a bit of background and going through some of their key features, and then the bulk of the webinar is going to be occupied by some hands-on demonstrations to really show you the power of this software in action. Before I get too much into the specifics of the two pieces of software that we're focusing on today, though, I'd like to spend a bit of time discussing the benefits of adopting what we call a simulation-led design approach. So, traditionally, simulation has been seen as a tool confined to the final stages of the design process. Steep learning curves and large time requirements have meant that whilst the value of simulation is clear, it's primarily been used in the latter stages, once the design has already been finalized. The aim of this session is to highlight how powerful simulation can be as a tool throughout the entire design process, guiding our designs rather than just checking them, accelerating the pace at which we can bring new products to market, and saving us money on costly prototypes and physical testing. Creo Simulation Live and Creo Ansys Simulation bring this powerful technology inside the familiar and easy to use Creo user interface, allowing for engineers to experience the full value of simulation-led design without the steep learning curve. So here I've got a flowchart of the kind of typical engineering design workflow, all the way through from concept to production. And the two products we're looking at today are mainly targeted at two different stages of the design process. Creo Simulation Live acts a bit like a compass in the iterative phase of the design process, guiding design engineers in the right direction in order to design better products quicker by providing immediate insight on potential design changes as and when you make them. Creo Ansys Simulation, on the other hand, is positioned a bit more towards the final design validation stage, with more accurate results and the ability to capture more complex behavior, but while still maintaining that ease of use that's afforded by being integrated within the Creo user interface. So I'm now going to take a closer look at each of these two products individually, starting out with Creo Simulation Live. With Simulation Live, you get access to Ansys's Discovery Live Solver technology, which uses GPU power to provide real-time results, allowing you to use simulation to guide and evaluate any design changes as and when you make them. Now, if you've used any kind of traditional engineering simulation tools in the past, this might sound too good to be true. As you'll see shortly, once we get into the demonstrations, however, the speed at which you can evaluate potential designs using Simulation Live really is quite remarkable. Simulation Live allows you to set up a number of different types of simulation, as you can see at the bottom of the page here. With a basic license, you'll get access to structural, thermal, modal, and even thermal structural coupled simulations. The Simulation Live Advanced license also allows you to access fluid flow simulations, allowing design engineers to quickly evaluate designs for a whole host of different applications in physics. As this diagram on the right here kind of emphasizes, Simulation Live is really handy for taking an initial design, quickly identifying any weak spots or areas for improvement, modifying the design, and then evaluating the effectiveness of your proposed design change. The pace at which you can do this means that you can evaluate loads of design iterations in the space of minutes, which is pretty much impossible with some of your more traditional simulation tools. Moving on to Creo Ansys simulation. With Creo Ansys, you get access to Ansys's flagship mechanical solver embedded within the Creo UI. This allows you to access the high level of accuracy afforded by the gold standard in simulation, whilst still maintaining an ease of use that puts this power in the hands of design engineers instead of exclusively in the hands of simulation specialists like myself. Like Simulation Live, there are two license tiers for Creo Ansys: the base Creo Ansys simulation license and the Creo Ansys Simulation Advanced license. With the basic license, you'll get access to linear static structural, modal, and steady-state thermal analyses, as well as access to common idealizations such as shells and beams. If you want to step the complexity of your model up a little bit, with the Creo Ansys Simulation Advanced license, you'll be able to set up more complicated models, allowing for coupled multiphysics and transient simulations. You'll also get access to nonlinear contacts and materials, allowing you even more confidence in the accuracy of your model setup, and hence in the accuracy of your results. For all but the most complicated models, Creo Ansys Simulation Advanced provides all the tools that a design engineer might need for validation. Despite this, should you need to access the high-performance computing power available in Ansys Mechanical Standalone, for example, or if you want to test a very specialized setup that isn't supported in Creo Ansys, you also have the ability to seamlessly export a Creo Ansys model into a setup file, which can then be read straight into Ansys Mechanical Standalone. Combining this with Ansys's elastic licensing model, which allows you to access Ansys software on a pay-as-you-go basis, we have a very powerful integration between these two softwares, which lets engineers access the more complex tools available in Mechanical Standalone as and when they're needed. So I'm sure by now you're sick and tired of just hearing me talking about these tools. So we're now going to jump into a couple of demonstrations of Creo Simulation Live and Creo Ansys Simulation in action to show you what they're all about. So to start with, I'm going to show you an example workflow in Creo Simulation Live. Hopefully, this demonstration will show you just how effective this tool can be in the early design stages of the product design cycle. Okay, so get started with the first demonstration now. And this demonstration is all about looking at some of the upfront simulation capabilities that we have using Creo Simulation Live. So to start with, we're going to go ahead and load up our model. And for this demonstration, I've got this kind of simplified compressor model. And we're going to say that the inlet is this small opening here. Outlet is the larger one at the other end. And in operation, this is going to be subjected to a high internal pressure. So we might want to start by analyzing the structural strength of our compressor and see how it's going to respond when it's subjected to this internal pressure. So the first thing we need to do is double check that we've defined our material. And in this case, we're going to use the FE40 material, which is in the default Creo material library. So we've got our material defined, and now we're ready to start setting up our simulation. And to get started, all we have to do is navigate to this Live Simulation tab. And you can see that we've now got this structure tree opening up on the left. And by default, it's going to load up a structural simulation. And we've got these two branches here for constraints and loads, which are going to be automatically populated as we continue with setting up our model. So to start with, we'll go ahead and define our constraints. So we're going to put a fixed constraint on the inlet here, which is going to stop it from being able to move in any kind of directions. And we will go ahead and put a displacement constraint on the outlet. And in this case, we're going to fix it along the Y and Z axis, but we're going to leave it free to move along the X. And if we look at our coordinate system down here, that's going to allow this outlet to kind of move along the X axis as the compressor expands due to the internal pressure. So if we enable our simulation objects display, that's going to show us where we've applied our boundary conditions. Lets us know that they've been applied as we intended. So in order to apply our pressure, I'm going to activate a section view, which is going to give us a view inside to allow us to set up our pressure load a bit easier, as well as giving us a bit of a better view when we look at our results later. So I'm going to set up a Z plane and come back to live simulation and set up our pressure load now. So I'm going to select all of these internal faces here, and I'm going to apply a pressure of 5 megapascals like so. You can see from our load arrows that it's acting as we expect it to. And now that we've got our boundary conditions and our load set up, we are ready to start looking at our simulated results. So to run the simulation, all we have to do is come up here to this simulate button. And in a matter of seconds, that was, I don't know, 3 seconds, you can see we've already arrived at our solution. If I turn off these simulation objects, we can get a better view. And it's important to note, I haven't sped up the video there. That really is just how quick Creo Simulation Live is able to give you results. And we've got a number of different results quantities to look at here. By default, it's going to load up von Mises stress, but we can also look at things like deformation. And if we want to, we can also animate this. So as expected, you can see the compressor kind of expanding under the load. And if we want to, we can change the scale factor, or we can leave it as true deformations, but it's going to be a very small deformation in that case. For the time being, we're going to go back to our von Mises stress, and we're going to modify the legend to be in megapascals. So you can see here we've got a maximum stress of 140 megapascals, give or take. And if we activate this button here, it's going to allow us to see the location of where this maximum stress is acting. In this case, you can see that it's on this sharp corner near the inlet, which we might expect to see a sharp stress concentration around a sharp corner like this. So in order to try and reduce this, what we might want to do is incorporate a round on this corner. So we're going to jump back into the model tab and use the round tool. And we're going to put on a round, leave it as 8-inch radius. And as soon as we hit OK, it's immediately going to start solving again. And you can see we've successfully managed to bring that stress down from 140 megapascals to around 110. So in this case, we would consider this probably to be quite a successful design change. We might, however, want to see if we can bring it down even further. If we jump into the Flexible Modeling tab, we can use the Edit Round tool to edit this round. And maybe we want to bring this all the way up to maybe 15 inches. As soon as we hit OK, once again, it's going to immediately start solving, giving us our results. And you can see now we've brought the stress way down, nearly half of what its original value was. So we consider this to be quite a successful design change. And this just showcases quite how quickly you can filter through potential design options. It shows how much of a powerful tool this can be for a design engineer, because setting up and running simulations, we've been able to evaluate multiple design possibilities in the space of just a few minutes, which is almost impossible with your traditional high fidelity simulation tools. So we've taken a look at our structural results, but what we now might want to do is have a look at the flow distribution through the compressor. So to do that, we're going to come back to the Live Simulation tab, and we're going to add a fluid simulation study. It's important to note at this point that fluid simulations are only available with a Creo Simulation Live Advanced license. However, with the basic Simulation Live license, you will still have access to structural, thermal, and modal analyses. So you can see we've now got our fluid simulation in the structure tree. And we've got this green icon showing that it's active. First thing we need to do is define our fluid domain. So that's going to tell Simulation Live where the fluid is actually going to be occupying in this model. So we've got a couple of options here. If we've already defined some kind of body in the modeling process that we want to use as the fluid domain, then we can choose this option here. If we were looking at an external fluid problem. So for example, maybe airflow over a carve. We might want to use an enclosure volume. But in this case, we're going to select internal volume because it's an internal flow problem. It's going to ask us to select our bounding surfaces. So in this case, that's the two faces at the inlet and the outlet. And it's going to immediately give us a preview of our fluid volume. That looks right, so we'll hit OK. We've now got this blue body that has been extracted from our geometry, and that is going to be our fluid domain. So next, we're going to assign material properties. In this case, we're going to use water. And all that's left to do now is to define our boundary conditions. So at the inlet, we're going to give it a mass flow rate of 1 kilogram per second. And in this case, we're going to define an outlet pressure of 0. We're going to say that it's exhausting to atmospheric pressure. So we've set up our boundary conditions like before, hit simulate, and we're immediately going to see it converging on a solution. And we've now got our steady state flow solution here. You can see a kind of high velocity plume coming from the inlet. And once again, there's a few different result quantities that we can look for here. And we also have a number of different results options when it comes to our flow analysis. So for example, if we wanted to look at streamlines, we can activate those. We can also change the number and the width of the streamlines. Similarly, we can activate particles. And this looks a bit busy, so maybe we might want to get rid of some of the slower moving particles. So we're just looking at the faster particles. We can do that by increasing this minimum gate. If we wanted to look somewhere in the middle, we could also filter out some of the really fast moving particles as required. We can also create a vector plot. And finally, if we want to look at this kind of swirling nature of the flow, we can activate the direction field option here. So another thing that we might want to do is we might want to probe the flow field for our flow velocity at a specific location. To do that, we'll jump back into the Model tab and define a point. For the sake of simplicity, we'll just put this at the origin of the part coordinate system. So you can see we've got our point defined here near the outlet. If we jump back into live simulation and choose the simulation probe option, we can select our point that we've just defined, check that it's looking for the right value. Yep. And you can see that we've now got our probe telling us that at that point, we've got a velocity of about 0.8 millimeters per second. Now, one of the really powerful tools in Simulation Live is this accumulate data option. If we tick this, then what we can then do is we can have a look at, for example, the effect of changing the relative sizes of the inlet and outlet. So if we come back to the sketch which we used to define this geometry in the first place, then let's say we could increase the size of the inlet to 15 and maybe decrease the size of the outlet to 30. So if we hit OK, like before, it's immediately going to start solving. And once it's reached a steady state, it's going to give us our new value at the velocity probe. Yep, here we are. So you can see we've now got a velocity at our probe location of about 0.74 millimeters per second. But what's really useful is if we click on this graph button now, we can see the values of the velocity probe for each of the two designs. And this is really handy because it means that you can compare the performance of various different designs um, and allow you to compare them and really evaluate which is going to be best for your final design. And simulation probes aren't unique to flow analysis. You can use these across any of the analysis types, and it's just a really useful tool for kind of evaluating and comparing different potential designs. Okay, that was a quick look at some of the tools at your disposal with a simulation live license. Next, we're going to explore an example using Creo Ansys simulation to carry out an analysis in line with what you might expect for a final design validation. So we're now going to take a look at some of the more advanced simulation capabilities that are available to us in Creo Ansys Simulation Advanced. Now, with Creo Ansys, we get access to the flagship Ansys mechanical solver. This is kind of the gold standard when it comes to FEA codes. And this is going to give you full confidence in your kind of final design validation. So we'll start by opening up our model. And you can see here, we've got this pipework model here, got a blank flange bolted on top, and it's going to be supported by these two lugs. And either end, it's going to be kind of bolted to extended pipework. So the first thing that we might notice is that down the middle here, we have some symmetry. And one of the considerations when we use a more advanced simulation tool like this is that we want to try and reduce the size of the model as much as possible because that's going to reduce our mesh size and allow us to get results a bit quicker or increase our mesh resolution if we like. So first thing I'm going to do is go ahead and cut this model in half. Okay, so we've got our half symmetry model now, and we're ready to bring this into Creo Ansys. So I'm going to navigate up to the Applications tab, click on Ansys Simulation. It's going to tell me that there's a mismatch in system of units. I'm just going to hit OK to convert them to be consistent. You can see here we've now got three options. We've got structural, thermal, and modal analyses. And these are the kind of key different simulation types that are available to us in Creo Ansys. For now, we're going to stick with structural, and we're going to turn off automatic contacts detection, which we'll talk about a little bit more later on. So the first thing that we're going to do, now that we've got this in Creo Ansys, notice that our tabs at the top have slightly changed. There's some new options to us. Most of these are in this Ansys Simulation tab, but we've also got a few options in our Refine Model tab. And to start with, I'm just going to apply a material model to all of the components in here. So we're going to use the same model for everything, and we're going to use this iron model that comes with the Creo default library. So now that we've applied our material properties, we're now going to look at constraining our model. So firstly, in the symmetry plane, we're going to insert a displacement boundary condition. We're going to scope it to all of the faces that lie on this symmetry plane here. And we're going to fix this in the Z direction and leave it free to move in the X and Y. And this is going to act as our symmetry boundary condition. On these two flanges at either side, where it's going to be bolted to further pipework, we're going to put a planar constraint. And this acts similarly to the displacement constraint that we've just applied. And it's going to allow them to kind of translate along their planes, but not move out of plane. Next, we're going to apply our constraints to the lugs to hold it up. And for these, we're going to use cylindrical constraints. See, we've got both of our lugs selected. We'll hit OK. So we've got our constraints applied. Next thing that we're going to do is apply our load. In this case, we're going to scope pressure to all of these internal surfaces here. And we're going to give it a value of 2 megapascals. Now, the last thing that we need to do is we need to define our contact behavior. So by default, because I unticked the automatic contact detection, it has no way of knowing how to treat these different components that aren't actually attached. So what we're going to do is go to the Refine Model tab and click on Detect Contacts. We'll set a small tolerance at 0.1 millimeters because all of our contact surfaces are actually touching. And we're just going to box select everything. We're going to stick with our default contact behavior of bonded. And now that I've hit OK, you can see in the window, it's giving us an indication of the contacts that it's applied. And if we come over here to our simulation tree, we can see that these bonded contacts have now been added in here. So we've got our model set up. The next thing that we might want to do is take a look at our mesh. Now this is one of the kind of key differences between Simulation Live and Creo Ansys, in that you have a little bit more control over your mesh generation in Creo Ansys. So if I come into the Mesh Control tab, I'll start by generating the default mesh, and we can take a look at what that looks like. So our default mesh has finished generating. So if I come up here and click Display Mesh, we can see what's been generated. This might be a relatively coarse mesh, but for the sakes of this demonstration, it'll be fine, and it'll keep our running times down a little bit. However, we might be concerned perhaps for these sharp corners in case we see any stress concentrations around these areas. We might want to increase the mesh resolution. So what we can do is come up here and apply a local size control. Select these edges, we'll select the ones on the outside as well. And we're going to apply a local mesh size of 5 millimeters. So now we can regenerate our mesh. Our updated mesh has finished generating. If we now display the mesh, we can see, as expected, we've now got better mesh resolution around these sharp edges, which is going to give us slightly more accurate results in these regions where we might be expecting to see elevated stresses. So we've finished working with our mesh. Now we're ready to get our first results. So all we have to do is come up here to the Run button. And one of the kind of helpful features in Creo Ansys that helps with just lowering that learning curve a little bit is when you come to run your simulation, it's going to automatically do a quick check and make sure that you've defined everything that you need to give you a kind of quick troubleshooting ahead of running the actual simulation. You can see we've got a warning about the geometry, but in this case, I know that's not going to be a problem. So I'll hit OK. And our study is now running. Okay, so we've just finished running our first sim. And if we come down here, we can see the processes in session. And if we take a look at a bit more info, we can see that this has taken about 30 seconds to run. So not very long, but that's been done with linear contacts and a linear material model. So you can see that by default, there's a number of results that will be automatically populated in the tree. And we might want to take a look first at the stress distribution. So you can see here, we've got our stress distribution through the pipe network. By default, it's going to show us the locations of our maximum stress and our minimum stress. And we might be slightly concerned by this maximum stress here. For example, if this material model has a yield strength at 200 megapascals, then we might want to look at perhaps using slightly more realistic material properties in order to capture some of that yielding behavior. So what we can do is come up here to our material assignment, and I'm going to duplicate this iron model. I'm going to rename it to FE40 nonlinear, and I'm going to change the stress strain curve to an elastic plastic curve. Now, you have the option here to define by tests. So if you have, for example, some test data, you could input that in here and it will be able to capture the same behavior that you've seen in your tests. I don't have any test data, so I'm going to untick this. I'm going to define it with a linear hardening law. And I'm going to give it a tangent modulus of about 1% of the Young's modulus and a yield stress of 200 megapascals. So, find my nonlinear material. What I might also want to do is perhaps look at the contact definition across this flange here. So at the moment, we've got it modeled using a linear bonded contact. And so that's going to effectively stick this whole flange across the blank flange on top. Now, this isn't going to be realistic. We would expect to see some separation in reality as this top blank gets pulled away from the flange by the pressure. So we might want to change this to a nonlinear contact to allow that separation to occur. So if I come in here and edit this contact definition, I'm going to change it to a frictional contact. And I'm going to give it a coefficient of friction of 0.2. So that's going to allow these faces to slide relative to one another up to the limit of friction based on a frictional coefficient of 0.2, but not allow any interpenetration between them. It's important to note that nonlinear contacts are only available in Creo Ansys Simulation Advanced. So I'll hit OK. I've now got my nonlinear material model and my nonlinear contact. So I'm ready to go for another run. So I'll come up here, hit run. So we've finished running our nonlinear model. And if we come into the process manager, we can see that this time it's taken just over 7 minutes to run. So this is quite a significant increase on the 30 seconds that it took to run with linear contacts and a linear material model. And this kind of showcases the fact that as you increase the complexity of your model with a high fidelity solution like this, your running times are going to increase quite quickly. But we've got our results now, so we can take a look at the stress distribution, for example. And if we go ahead and define a contour plot of the contact status and scope it to contact 11, which is our frictional contact, we can take a look at the contact engagement. And we can see now that if I remove the deform shape, we're now getting less even contact, as we would expect, because we would expect to see some separation. But we've got some kind of slightly uneven contact around the bolts. This might be an indication that maybe we'd want to look at refining the mesh in this area. We'll also go ahead and define another stress plot. And if we update these results, this is going to allow us now to modify legend. So we can set this upper band to the yield strength. And we can now see if we set everything that's red to be above yield, you can see that we might be quite concerned, particularly with this blank flange, that we might see some significant yielding going on in this part now. So another option that we have with the Creo Ansys Simulation Advanced license is to include some thermal effects. So if I come up to Setup here and tick Include Thermal, you'll see that a number of new options are available to me. So I've now got different thermal boundary conditions. And this will allow us to model the stress effects of differential thermal expansion caused throughout the part by different temperatures. So what we might want to do, for example, if we scope to these internal faces, a temperature of, say, 100 degrees C, if we've got hot liquid flowing through this pipe. You can also scope a convection boundary condition to some of these external faces. Just leave it as that for now. We'll give this a convection coefficient of 500 watts per meter squared Kelvin, and we'll say that that's at room temperature. So we might want to see the effects that this thermal distribution has on its own on the stress distribution. So if we suppress our pressure load, we can now run. You can see it's now giving me a new warning that I haven't defined any structural loads, but because I've defined these temperature boundary conditions, I know that that's fine. So I'm ready to go ahead and run the simulation again. Okay, so we've finished running our thermal structural simulation. So now we can go ahead and take a look at the results. If we look at the stress distribution, for example, we can see that we've got quite high stresses occurring on these sharp edges, as we might expect to see. And we can have a look at the kind of deformed shape, see the expansion occurring as a result of that differential temperature. We might want to take a look at the resulting temperature. So you can see if we come up to define our results, there are a number of new results types that are available to us. Now we'll stick with just a standard temperature plot. And if we update our results, you can see our resulting temperature distribution. And as we would expect, it's hottest on the inside where we've defined our temperature. And on the outside, we've got some cooling because of that convective heat boundary condition. So that's a quick look at the thermal structural capabilities that are available in Creo Ansys Advanced. It's worth noting that I suppressed the pressure load in this case, but you can run this with any combination of temperature and pressure loads. You don't have to just stick to one type of boundary condition. Now, the last thing that I'd like to showcase is the link between Creo Ansys and Ansys Mechanical Standalone. So if you, for example, wanted to use some of the high-performance computing capability that's available in Ansys Mechanical Standalone, or maybe some of the more complicated boundary conditions, then you might want to take this model and work with it in Ansys Mechanical. Now, there's a really nice, easy integration here. All you have to do is come up here to File menu, click on Save As, and that's going to give you the option to export to Ansys Mechanical format. And if we export this file, just like that, it's exported our whole model setup, and we'll then be able to go ahead and open that up in Ansys Mechanical. So now that it's finished recording that caststat file, all we have to do is open up the folder that we saved it in, double click on it, and that's immediately going to open up a Workbench project, and it's going to import all of this data that we've set up in Creo Ansys, and that's going to allow us to work on it in Ansys Mechanical. So as you can see, it's generated a couple field static system because we've enabled temperature effects, and it's now just going to go ahead and gather all that data and input it into Ansys Mechanical. So as you can see by this green tick, it's now finished reading everything in to Mechanical. And you can see that we've got our model set up as we set it up in Creo Ansys with all of our boundary conditions. And this is going to allow us to use all of the functionality within Ansys Mechanical to do whatever we might need to do outside of Creo Ansys. For example, utilizing the HPC capabilities, or just using some of these more advanced boundary conditions. So just there, we've taken a quick look at some of the tools that are available in Creo Ansys Simulation Advanced for final design validation. Hopefully you've been able to see the power of this piece of software. And whilst we looked at a fairly simple example for the sake of this demonstration, you can really extend everything that we used today to model to some really quite complex situations and loading conditions. On top of all of the features that are available in Creo Ansys Simulation itself, we also took a look at the integration with Ansys Mechanical Standalone, and this really shows that the sky is the limit when it comes to what you can capture with Creo Ansys. Okay, well that brings us to the end of our look at Simulation Live and Creo Ansys. Thank you all very much once again for joining us on this webinar, and don't forget to sign up for the final webinar in this series, What's New in Creo 12, on the 18th of June. With that, we'll conclude, and if there are any questions, we can address those.
Great.
Great.
Thank you, Oshin. Maybe I've got a bit of feedback here, sorry. Yeah, just wanted to sort of just conclude and remind people we've got a final webinar on the 18th. We also ran one last week, which is a bit more detail into Ansys. So if anyone's interested in understanding the scale and the capability of Ansys Mechanical for structural simulation, myself and my colleague Mohammed Moeen did that last week. That recording should be available. And we also have some webinars in July, September, and October, again, focused on other areas that Ansys can deliver and that PDS can deliver on simulation involving electromagnetics, fluid mechanics, and optics. So once again, thanks for everyone attending. There will be a recording of this. We'll get in touch. But if you've got any questions, as Oshin said, let us know. Reach out to us. Reach out to myself and Oshin or your local sales contact regarding any questions or if you want to investigate this further. So once again, thanks everybody. I'll just say cheerio. Bye-bye.
Thanks, guys. Thanks for joining us. I'll close out the session now, but don't hesitate to get in touch if you have any further questions. All right.